We're going to go over a little bit of chemical bonding from creating a salt, Born-haber cycle, Coulomb's law, formal charge. We're going to talk about molecular geometry. We'll talk about the orbitals that are involved in those bonds, and then we'll talk about some bond energies as well. First, many problems give you a lot of information before you even start. So this is a great example of that. You may have seen this before, and it'll tell you a process, and it'll tell you the enthalpy associated with that. Please be very familiar with these terms like sublimation. It's a phase change. First ionization or second ionization energy is removing an electron or removing another electron. Electron affinity is about gaining electrons. And then finally, one that may escape you is lattice energy, is the amount of energy that is released when two gaseous ions form a bond and release a ton of energy. And all that together equals enthalpy of formation, the amount of energy it takes to create 1 mole of a substance from its elements at standard conditions. Well, instead of using the numbers, let's just talk about creating a overall description, a Born-haber cycle. So I'm choosing calcium nitride. So notice on the top, first, this is the equation that you need to have an understanding about. It is the enthalpy of formation, okay? And we're going to move that over there right now. That is enthalpy of formation. I'm creating 1 mole of the salt from its elements at standard conditions. Okay, but what do we all need to have? The hidden chemistry behind all of this is really the most important part. And what is that? I stated just a few minutes earlier, is that I am making my salt from its ions in a gaseous state. So I think it's really important to have an idea that I need that at the bottom of my cycle, of my chart. So I have my Ca2 plus, I have my N3 minus, and notice that I have to have them balanced with what the salt mole ratios require. So let's talk about each column here, from the Ca solid to the Ca2 plus ion, and from the N2 gas to the N3 minus ion. There needs to have some things occur. I need to get that solid into a gas. I need to get that gas into an ion, and so on and so forth. So why don't you pause the video and attempt to make arrows going towards those ions from the solid and the gas in the top, and try to show me the process that occurs 1 step at a time. If you can do that, take a pause. If you did it right, this is more or less what the calcium should look like. I went from a solid to a gas, from an atom to an ion, and then an ion with a greater charge. The nitrogen should look very similar. The only difference is that it's already a gas, but I have to break apart that diatomic, and then I need to be adding 3 electrons instead of only removing 2, which the calcium did. Now I'd like you to pause it and place all of these, each process on the appropriate line. So for example, I did this one earlier. This is enthalpy of formation. Every one of these red lines, it has a corresponding purple box to the left here. I think it's very important that you have an understanding of where they all would be located. Normally, when you're doing something like this, they have a corresponding energy already, but this exercise is more about just understanding the overall layout of the Born-haber cycle. Give it a shot. Pause your video. All right, let's see how we did. So let's just do it in order here. I'm going to do all the calciums first. So from a solid to a gas, I hope that we would recognize that that would be sublimation. Calcium to calcium plus, that is the first ionization energy. And plus to 2 plus, hopefully that would make sense that that is the second ionization energy. Sliding over, N2 to 2N gas. This can be named multiple ways. So this one, your option was bond energy. Sometimes you will see dissociation. That is the same thing. So you do need to get very familiar with that. And why there's a 2 there is if you break up N2 into 2 nitrogens, then you would have 2 of those there. So you have an N bond into another N. The result is you have 2 N molecule or atoms present. Going from 2N to 2N minus, you are gaining an electron. That's electron affinity. Then you gain it again. And ultimately, you will gain it again. Please know that if there is a coefficient above one of your purple boxes, when you place your enthalpy that's associated with that process, it must reflect the number of moles, which is your coefficient. So bond energy, for example, the energy associated with that would not have created a factor by a mole coefficient. It would just be whatever the value is. But with the first electron affinity, I have to multiply that value by 2. Lastly, the greatest release of energy is after I take my 2 ions, I will have an attractive force, and it will be called the lattice energy, which releases all of that energy to create that really strong ionic bond. Next, let's do a little matching. We're going to talk about the strength of a salt based on its formula. So predict the binary ionic compounds and match their lattice energies. So before we can start doing our matching, we need to actually figure out these formulas. So pause the video and look up the charges of each of these ions and create an ionic formula. So for example, Mg would be 2 plus and Cl would be minus 1. Create these formulas. Then we'll have a bigger discussion in a moment. So if you did it right, these should be my formulas. MgCl2, Ca3P2, BaBr2, and SrBr2. All right, now we're going to match these lattice energies. Now these are not necessarily real. These are representative of different strengths. So I am gaining lattice energy as I move down from 2,500 to 12,000. I have parts of the periodic table up here to help you figure this out. So what are we doing? This is the goal. We're talking about lattice energy. So then that means we're talking about Coulomb's law. Right? And Coulomb's law is simply the charge or the size. And which one has a greater effect? The charge does. So usually what you should do is quickly look at the charges. So let's do that together. I have a plus 2 and a minus 1. I have a plus 2 and a minus 3. I have a plus 2 and a minus 1. And I have a plus 2 and a minus 1. The ones that factor a largest value for charge will have the greatest lattice energy. So you can see that 3 of them have a plus 2 minus 1, but one of them has plus 2 minus 3. So that one will be done. So this is based on charge. That is the reason that I can place that. The other 3 must be determined by size. So if we just take a look at this relationship right here, mathematical relationship, the smaller the size, the larger this value. So take a moment, look at the periodic tables in the, or sections of them in the left and the upper right corners of the screen, and can you determine where all 3 of these should go? So pause the video and try to determine that on your own. By taking a look at the sections of the periodic table, it is quickly determined that my Mg and my Cl are the smallest. It's the smallest cation for the Mg, and the Cl is the smallest anion for the anion. So this has to be the strongest because it is the smallest. So then it comes down to Ba, Br2 and SrBr2. The BRs are the same, so I don't have to look at that. So now I simply look at the strontium versus the barium, and the strontium is much smaller by an energy level, so Sr is smaller than Ba. So that should be the order of my salts with their lattice energies. So these were all determined by the size or by the radius and not by the charge. Let's talk a little bit about resonance and formal charge. So resonance structure is a structure that has more than one possible Lewis structure. Many times it's more about moving in multiple bond around than it is about moving the atoms around. So if we look at NSC, first off, what can be confusing about that is that that is not actually how the molecule looks. The center atom would be carbon. Whenever you see carbon, you think center atom. First, we have to determine what this all looks like. So as a review, we usually use a method called TV, and TV gives us the ability to know if it needs extra bonds. So if I reveal what that is, I basically draw the skeleton of the structure. Then I count up the number of electrons, and I got 20. I count up how many valence electrons I should have, which are the numbers underneath my formula, and that comes out to 16, so it's a difference of 4. So what does that mean? It means I need 2 extra bonds. My picture has 4 too many electrons. So if you look at that structure, how many different ways can I draw that if I add multiple bonds to that on the right structure? If you're only thinking one, what you're thinking is very much a symmetrical fashion of distributing those bonds, which is great, but it's a resonance structure, so it must have multiple ways. So I can place them both on one bond or the other. So hopefully you're thinking 3 different structures, and that's what that would look like. So now we need to do formal charges. Formal charge is when you take the number of electrons that an atom has, and then you subtract the sum of the unshared electrons, or the number of electrons that aren't in a bond, plus the number of bonds, or formally you would say half of the shared electrons. So if I did that for just one of them, that's what I have for that nitrogen. It's 5, which is the number of valence electrons that nitrogen should have, minus 2, which is the number of unbonded electrons, plus 3 bonds, or half of the shared electrons. So that means that my formal charge is going to be 0 for that. What I'd like you to do right now is I'd like you to try to figure out all of these other formal charges. So pause the video and work on all the other formal charges for all the other atoms. Little reminder and hint is if one of those atoms bonds the exact same fashion with the same number of bonds and or the same number of lone pairs on it, you do not need to keep repeating finding the formal charge. You can just assign the formal charge to the remaining atoms within the other structures. So give it a shot. Pause the video. So here is my work for all of the other atoms. And what we can do then is assign what values there are. So this carbon one, this is the value that I was kind of hinting towards, that they're all probably the same. Here's another little trick, is that let's say you didn't know how to do the sulfur if you weren't sure if you did it right or not. This whole structure needs to be -1. So the very fact that I have 2 zeros already means that this last one has to be -1. And if you do look at the math, 6 minus 7 is -1. But it's a nice little tip. Same thing here. If that's -1 and my center atom 0, it would make sense that this has to be 0. So those are all my formal charges. So how does that apply, and how does that help us figure out what is the best resonance structure or the most favored resonance structure? Well, we can talk about a couple things first, which is the least favored resonance structure. It's going to be this one. And the reason why is because I have a 2. I have a -2. And there's a couple things with that, but the rules with formal charge is that our goal is to have it be zero. And if we cannot be zero, is that the most negative of the formal charges should be on the most electronegative atom. And if you look at a periodic table, sulfur is actually more to the upper right than nitrogen. So sulfur is more electronegative, so that can have a positive one, but twos are not good. So it comes down to these two. And if you look at it and you're unfamiliar with formal charge, it may look like it's a horse apiece, but it is not. Because of the fact that the sulfur here has a -1, it is more electronegative. Now, you could look up the values for sulfur versus nitrogen, but sulfur is more to the upper right, closer to fluorine than nitrogen is. So that is why I would choose that structure. Molecular geometry. Molecular geometry can be very tricky because you do need to be very familiar with it. But if you keep it straight that we are working with 5 parent geometries, so the 13 or the 14 structures that you're required to know all come from 5 of them. But you still need to be able to figure it out based on the formulas. So let's go through one together. So ClF4, what you should do is first just think about what that looks like. So when I draw this, what I'm really doing is I'm acting like each line has that fluorine on it. But it doesn't need to be drawn like that right now, because all I'm wanting it to be is that idea of how many electrons are bonded. What if it all had single bonds? If it all has single bonds, that's going to be TV. So T is that line with the F's, that's worth 8, so there should be 32. I have 7 plus 7 times 4 plus another 1. That should be 36. So that's -4. What does that mean? It means that you need 2 extra dots. What's the big deal? Your whole goal is to find the steric number. How many electron clouds you have. I have 6 electron clouds. The minute I say 6 electron clouds, my mind goes to what molecular geometry, what parent geometry do I need to draw? So in this case, 6 has a vertical axis with a perpendicular square in the middle. Now I assign my atoms, and I want to be as symmetrical as possible. I understand that lone pairs take up more space, and they will be as far away as possible from each other. So if I put them on top and bottom, that's what that's going to look like. So we have some things that we could answer. Parent geometry, that is octahedral. Molecular geometry, or actual geometry, is omitting the lone pairs. So if I imagine that those are not there, or I just highlight them so they are not part of my actual drawing, is that that's very flat, so it's plane in a plane, and it looks like a square. So that is a square planar. Hybrids are based on the number of bonding, or number of clouds, or the steric number, which creates the geometry. So I have 6 clouds. So that means it's sp3d2. It takes electrons from an s orbital, 3 p orbitals, and 2 d orbitals, and that equals 6. Bond angle, more or less, it's 90 degrees. You could argue that there's a 180 as well, but between each atom, it's approximately 90 degrees. Lastly, polarity. You should be able to show it. So I'm going to do it right on my structure once, is that all fluorine atoms will be the ones that pull the most. So the very fact that when I look at that all those dipoles are pulling in opposite but equal directions, that would tell me that this is non-polar. We're going to make a little change. Instead of having the XeF4 and the SO32 minus, let's try N2O and SnCl5 minus. Little hint with the N2O is that the N is a center atom. So when you're thinking about it, you'll want it to start like that. Okay? So give it a shot. Try to determine these other two molecular geometries and the information that goes along with it. All right, let's see how you did. First, before I move on, the first problem, we needed a bracket with a charge, so that was just my fault on that. Don't forget about that. So if I determine this shape, what I would do is quickly assign, either mentally or actually writing it out, everything with a single bond. So that would be 20. But I have 10 coming from this, 6 from here, so the difference is 4. Not negative, positive. So my picture has 4 too many electrons. So a good rule of thumb is when it's negative, you have to add them. When it's positive, you need to take away electrons from that center atom. So if I take away, I need to really take away both of these pairs, and I need to replace them with bonds. So what it's going to look like will be that. Now, I technically probably have a resonance structure here where I can draw triple bonds and single bonds, but we are not asking you to do a resonance structure right now. So what does this result in? It results in 2 clouds. So that has the following information. It will be linear. There are no lone pairs, so it has to be linear as well. There's 2 clouds, so it's an SP. The angle is 180. And as for the bond dipoles, or the polarity in general, is that, that nitrogen can't pull more on itself, but oxygen will. So in general, this has a molecular dipole moment. So this has to be polar. SnCl5 minus. Quickly, let's attack that. If I do that, I have 40 for single bonds. How many should I have? A good question would have been, what is tin? Well, if you just look at where tin is located, it is located on the 4A column. So that is actually what we're going to assign it as. So this is 35, and this is another 1. So that's 40. It's 0. What does 0 mean? 0 means that we do not add any electrons or take any electrons away. So we simply have 5 electron clouds. The minute I say 5 clouds, I think a vertical axis with a perpendicular triangle. And then I assign all of my atoms. So this will be my structure. What does that all mean? This will be a trigonal bipyramidal. No lone pairs on any of the bonding areas. So it's another trigonal bipyramidal. There's 5 clouds, so it's sp3d. The bond angles themselves are 90. And then in between each atom on the triangle is 120. Some people will also say that this right here on either side is also the 180. So you could include that. That's not as important to me. And then finally, is this polar or nonpolar? Well, it is completely symmetrical. This is nonpolar. Just so you've seen it, if I had to show bond dipoles, is that the chlorine pulls more than the tin. So it's going in 5 opposite but equal directions. So those are some things that you'll have to be able to answer on any molecular geometry problem. If you have a structure known or unknown and you are able to draw it out, can you discuss the orbitals that are involved in the bond? So when I look at this, there are many things that I can interpret. And one is the number of clouds. So for example, my carbon has 3 clouds, a steric number of 3. So if I asked you for the hybrid, you'd say that that's sp2. If you looked at the sulfur, it has 3. So you'd say that that's sp2. And if you looked at the chlorine, which actually has this on it, you'd say that that is sp3. And finally, to wrap things up, is the hydrogen, because it only has one cloud. It can't even hybridize, because to be a hybrid, you need two things. It's a 1s. So those hybridized bonds are what we call sigma bonds. So I don't need to necessarily be this official on it, but I'm going to be, is that the sigma bond between the hydrogen and the carbon would be a 1s for the hydrogen and an sp2 for the carbon. For this bond, I have two of them. I have a sigma and I have a pi. So between the carbon and the sulfur for the sigma, it's an sp2 from the carbon and an sp2 for the sulfur. For the carbon, and we'll come back to the pi. For the carbon and the chlorine, we just have a single bond, and that's an sp2 to an sp3. So what's going on with the pi? I'm going to attempt to draw this. It won't look very good, but just between the carbon and the sulfur is I'll have a carbon atom here and a sulfur atom here. And what's happening with that carbon atom is that you have three these are going to be my sp2s. Let's get that out of the way. I'll say sp2 here. And then my sulfur has the same idea, an sp2. What's happening is that these are sharing electrons right here. Like over here, this is sharing an electron with my hydrogen and my chlorine. And then over here, there are just two lone pairs right now. But there is another bond there. And that bond is a hybrid. Is an unhybridized p orbital. It's not the greatest drawing in the world, but what it does is it's going to reach up and over, and it's going to create a pi bond. So a p orbital, though, is very important to understand that it comes from the valence electron of that specific atom. So carbon is in the second period of the periodic table. So that's why it gets a 2p. But sulfur is in the third period of the periodic table, so that needs to be a 3p. So that's how that correlates to bonds and their orbitals. Lastly, we look at bond energies. And you need a bond energy sheet that looks a lot like this. You'll notice that it is organized by atoms, and it gives the amount of energy it requires to to break that bond. That is the same amount of energy that is released if that bond is formed again. So these are all positives because we are breaking the bonds. Please note on the right are all of my extra or my multiple bonds. There's one exception, the CO with an asterisk, 749. It actually refers to the double bonded CO in CO2, and that is actually not 745 anymore, it's 799. So taking a look at that, we have these two equations. So the first thing that is so important is that you need to understand what it actually looks like. So I will do the first one with you, and then you can work on the second one. You need to understand the exact bond that's happening. So for example, HCN. That is not all that's happening. We know that carbons like to bond 3 times. So this is what's happening on this one. H2 looks like that. And then finally, this structure looks something like this. So you need to be able to count up the bonds. Remember that we have to break the bonds first, and then you have to form the bonds. You have to break them before you make them. So that's why we have to subtract. So you're going to take all those values, and then you subtract the sum of all the other values. So take a look at your bonding energy sheet and count up all those bonds. And let's see where we're at after we pause this video. So this is the breakdown that I have for just the bonds themselves. I believe that this notation is extremely important because you are showing the reader what bonds exist. Please note a couple things, that when I have two of them, I need to have two. When there are three of the same bond, I also have to reflect that. So if there were a coefficient in front of that structure, I'd have to multiply that 3 by whatever value that is as well. So now I'm going to assign my values. So I get 2168 kilojoules that are required to break all those bonds on the reactant side, and it takes 26 kilojoules of energy released. That's why there's a subtraction. To release all those bonds that are formed. So the difference then, my whole reaction is negative 158 kilojoules. So take a chance at the next problem, please. Take a look at it. Pause the video and work on the combustion of propane down below. If it's a combustion reaction, hopefully our answer is negative. That means it's exothermic. It can be a positive answer, then it would be endothermic. But in this case, combustions are usually releasing quite a bit of energy. So pause the video and give this one a shot. And looking at my work here, you may have realized that you have forgotten to balance your equation. That is something that you have to really make sure you've done. In the first problem, why I didn't bring it up at all, is that once you see a coefficient, you know it's automatically balanced. No one half balances any reaction. It's either balanced or it's not. If you don't see coefficients, you want to make sure that you check that. So I was seeing if you were going to remember that or not. If you didn't, at least you've made all of your bonds, and now you can address the coefficients and the number of moles of each bond that you have present. Just to point out something, for example, the CO2, because I have two of them, and there's 4 CO2s, that's why it results in an 8. So I'm going to assign my values, and I'm going to see what I get. Here are my values. The one to point out is the CO2 value. If it's a C double bonded O, it's normally 745, but because it is in carbon dioxide, it is 799. Overall, 6,473 kilojoules of energy went into breaking bonds, and 11,062 kilojoules were released by forming bonds, which makes a grand total of negative 4,589 kilojoules. Hence why combustion of propane is such a good reaction for producing energy, because it releases so much of it.